Okay, fair enough. Okay, so anyways, welcome back. So we'll keep talking about the theory of Poisson boundary and what are the criteria for identifying the Poisson boundary indeed. And so the main question, as I said already many times, is we start with the measured group, G mu, measured countable group. And then we have this mysterious space, the Poisson boundary, so such that BP Poisson first represent as PF, such that there is this magic duality between H infinity of G mu, which is canonically isomorphic to L infinity of VP mu P. But now, the first question would be, can we tell, is there a criterion to tell whether the boundary is trivial? So for instance, whether this BP mu P is isomorphic as a measured G space. So it's a measurable space with this measure is isomorphic to just a point with the delta x. Meaning that basically, if you look at this ergodic component, so you recall that the way we discussed is like you define BP mu P as this complicated quotient. So we start with omega, which is the space of infinite sample paths, in with quotient with the shift. And then we have to take the space of ergodic components. So this quotient is a complicated part. But basically, we want to say that in this space is the space of ergodic components only one point. There is no other way to partition omega in unions of measurable classes that are also T invariant. Unless, so the only way to do it is to have almost every element to the same cost. So that's the triviality of the boundary. And so fortunately, so again, and
sorry, can you say sorry, a way to compose the set into what that's T invariant?
That's right. So basically the point is that you want to say that if right, so this boundary is trivial point. Well, this basically means that every way, so you'll have the set omega, which is the space of infinite sample paths, and you want to write this space omega as union of T orbits. And in a way, so such that every class is a union of T orbits, and it's also measurable, right? So it means that the only decomposition, and try to write it like that, of omega into measurable and T invariant. T invariant sets right, so that the quotient is a Lebesgue space. Basically the only way is the trivial decomposition. So basically, is to assign full measure to one class. Now this is a remember that what we discussed before about. So recall the analogy with the rational rotation of the torus. So we have this analogy that if we take an irrational torus rotation, so we have classes. So each orbit is a leaf of this foliation. But if you identify as equivalence class each leaf of this foliation, then every equivalence class has to be a union of such things. But every invariant set, which is measurable and a union of classes, has full measure or zero measure. Right. So recall that here our classes are, so our leaves of the foliation. And so the point is the only way, so any measurable set that is union of classes as either zero measure or full measure. Or full measure, and this means that in this measurable category, if we want to take the quotient, there is no other quotient you can take. The only possible quotient to take is to pick one such class of full measure and say, okay, this is the atom of our measure, and that's it. So the only quotient is isomorphic as a measure space to point with the. So if we're in the same condition, so there's a godicity here of this map that applies. And so similarly here, so you cannot decompose the space of infinite paths into equivalence classes in any measurable way unless you give full measure to one class. And that's that's equivalent to the triviality of the boundary from the point of view of the body. So this is a tricky point, but that's the important point. Any questions? So again, this is the reason why we need to introduce another technique is because this is really hard to get your hand on. And that's why we introduce the entropy criteria. Which is definitely a bit more easy in a sense of like you can compute some numbers. So here you're not computing anything yet. You just have this equivalence relation. It's like very, very soft, but also hard to manage. So the entropy criterion again has been proven by Kamenovich and Vershik in the I think around 83. It's in this famous Kamenov paper, and there's also about at the same time another paper by the Riet. So these are sort of independent, but the criterion is the same. And so the criterion is really nice. So let's again a G mu, a measure group. And with finite entropy, so h of mu is finite. We will recall what the properties of entropy were. We already mentioned it last time. And So the theorem is the following. The Poisson boundary of G mu is trivial, meaning it's isomorphic to a point, meaning there are no non-constant bounded harmonic functions, if and only if this asymptotic entropy h, small h of mu, the limit of h of the nth convolution of n with itself, and so this limit that always exists if h of mu is finite. So this is one of the homework problems. So if and only if this is 0. So this is super simple. And it's much easier to control this quantity. Okay, so now so the goal of today's class is to prove the entropy criterion. So then eventually there will be also a relative version of the entropy criterion, because okay, now this classical one only proves whether the boundary is trivial or not. It does not tell you whether a given geometric boundary also is the Poisson boundary, in the case it's not trivial. But in fact, this entropy technique can be made into a relative version, and then you can also produce identification of Poisson boundary for the non-trivial case. Okay, so let's see a few things. So I think last time we gave at least a definition of entropy. So okay, so recall. So let mu be a probability measure on G. Let's say G is countable. Again, in fact, the entropy theory for locally compact group exists. In fact, we proved the version of the entropy criterion recently for locally compact groups. So these things are still active areas of research, but actually, but anyways, but for this course, we will just focus on the slightly easier case, which is the countable case. So, okay, so the entropy we know already what. But the formula for entropy is simply the sum of minus mu g log mu g and again, the idea is that this is the information. This is the information that is given once you're performing your experiment in G has your space of all possible outcomes is G. So you pick a random element, and then if the probability of some random element is very small and you happen to pick it, then the information you're gaining is very high. So that's why it's minus log of G. Obtained by observing, let's say, G itself. And then, so again, so we assume that this is finite. This is the sort of the weak point of this theory, that we need the finiteness of mu. Of course, many times we are interested in the simple cases, like if the measure is supported on a finite support, then of course the entropy would be finite. But in general, the support of mu could be infinite, and in fact, there is examples where this entropy could be. So that's somehow it lies. But so we saw lemma that we approved last time, which is classical sort of variational principle. In this case, is very easy to state, is that if, yeah, let's say that if the support of mu has n elements, then, well, in general, so that h of mu is less or equal than h of the uniform distribution, which is log n, where mu is, again, is 1 over n, the sum of the delta of g. Then g is in the support. So here we have that you can fix the support, you can change the weights that you're given, different elements in the support. And it turns out that the highest possible value of the entropy is reached when all the weights are the same. So is the uniform measure on the support. Right?
The sum is over G in this.
Yeah, the sum is over G in the support. Yeah. So the proof of this we saw is just a classic convexity property or Jensen's inequality. So the other properties of entropy. Well, first of all, the entropy of, if you take mu1 and mu2, so sort of we take tensor product of mu1 or mu2, so these are two independent measures, then this is entropy of mu1 plus entropy of mu2. So here, mu1, mu2 are independent. On the product space. The second is under projections, the entropy can only go down. So if you have a map pi from x mu to y mu, or maybe, okay, let's call it G and H, maybe since we call them groups. At this point, we haven't used the group structure yet. So this could be for any finite set. So is surjective and measurable and pi star mu equals mu, then the entropy of mu is less or equal than the entropy of mu. I mean, it's kind of clear because we're collapsing certain elements of G to elements of H. So for instance, the easy thing you could always do is collapse everything to a point, then obviously the entropy would be 0. And in general, you may lose some information by collapse. So that's all good. And now, so the exercise that I put in the lecture, in the problem set, so we'll spoil it, is if you let Hn to be H of mu n, so you're taking the n star convolution of mu on itself. So now we're starting to use the group structure. Then, first of all, you have this subadditivity property, h of n plus m is less than h of hn plus hm. And then once you have that, then you can produce, then you know by Fichte's lemma that there's a limit. Right? So h of mu small h limit of h m over m exists. Moreover, also a small hm is smaller or equal than big hm. This is also classical from the subadditivity. So, well, so this is called H mu is called asymptotic entropy or Abet's entropy, because it was introduced by Abetz, I guess. So H of mu is called asymptotic entropy. Or Abet's entropy. Okay. Now, clearly, entropy also has a relation with the growth rate of a group. So if G is a finitely generated group, and you take S, let's say we take S in equals S inverse a finite generating set, then well, then we can define the word metric on G by saying that the norm of G with respect to S is the infimum of all the K's such that G is written as a word in the generators. So this is called the word metric. Of G with respect to S, so it does depend on S. However, it depends on S so in somewhat weak way, because lemma is the following, that if S and S prime are finite generators generating sets for the same group G, then there exists some C such that the norm of G with respect to the S prime norm is less than C S, no, sorry, C G S plus C is smaller than 1 over C G S prime minus C for that. So the norms of G with respect to the two different generating sets are not the same, but they're bounded by multiplicative and an additive constant. So it depends on the problem. So for some problems, this is not good enough, but for some other problems, this is the case. In fact, we say that these two metrics are quasi-isometric to each other. Okay. But the word metric for S and the word metric for S prime are quasi-isometric to each other. And once we have the notion of word metric, we can have the notion of growth of the group. So find the growth function of G, again, with respect to S is what? Well, gamma GS of N is the number of elements of G that have norm with respect to S at most M. Is the ball of radius N in this metric. And then the growth rate is small gamma GS is lim sup or limit, actually, I think, well, let's say lim sup. I think you can actually take the limit of gamma GS N 1 over N. So with these balls, so we expect these balls to grow maybe exponentially with the radius. And so this would be indeed the actual number. So in fact, we can see some simple examples that we already know, maybe. We take G ZD, and S is a standard generating set. So you're moving again. You do it is like the ones that generates the simple random walk, the dimensional grid. Then what is gamma of G S N? So what are the elements that can be reached in n steps from the origin, right? Yeah, so they're like it's the ball. It's like depending, okay, so depending on, okay, yeah. Okay, so actually not this ball, right? So suppose, yeah, so suppose, I don't know, suppose you take n equals 2, right? Then you get this guys. Okay, how many how many there are in this case? Yeah, I think in this case, yeah, in this case, there are 13, which is 1 plus 4, right? This is 1 plus 4 plus, yeah, it's 9 plus 4, yeah. 1 plus 9. Yeah, so in general, yeah, in general, how many are there in ZP? So for d equals 1, right, gamma GSN is what? 2n, it's not 2n. For n equals 0 is 1. For n equals 1 is 3. Okay? Not quite 2n. I think it's 2n plus 1. And it's not so important, but you know, just for fun. So for d equals 2, what's the actual count? Okay.
2 squared plus 3 squared plus 5.
Right, so let's see, right? So here for n equals 0, we get 1. For n equals 1, you get 5, right? Which is 1 plus 4. For n equals 2, you get 13, which is 4 plus 9. So how many for 3? Right? So if you do another one, you will get another diamond like that. Right? So there is an odd square, which is not 3 squared, and there's an even square, which is 4 squared. Right? So what's the right number? $35. 35, yeah, exactly. It's not like 6. Okay. So for n is what? Is n squared, I think, plus n plus 1 squared. So I think for d equals 2, this is 2n squared plus, yeah, plus 2n plus 1. Yeah, anyways, it's not so important to see what is the right number. We're only talking about the growth rate, but it's actually kind of a nice exercise. So in general, this is the order of n to the d. Now the question is also, what is this constant? Is it always 2? It's an interesting question. This is to think about. But okay, so of course, what we want from here is that gamma, of course, gamma of GS would be 1. So clearly, if you have abelian groups, then the rate is small. So of course, we call group G of sub-exponential growth if gamma GS equals 1 for some but in fact, equivalently, any S. Right, so yeah, this is called also group of polynomial growth. Yeah. This could be called group of polynomial growth. Yeah. But for the moment, yeah, in some sense, we. Yeah, no, I mean, in fact, there is group of exponential and and exponential and of exponential growth. If gamma S is bigger than 1. And yeah, indeed, there is this interesting class of groups that are neither of polynomial growth nor of exponential growth. So the kind of in between, this is famous groups of intermediate growth. And okay, these are very, very interesting groups. But yeah.
You can't say anything like if it's just if it's greater than 1.
Right. So I mean, if the group is finitely generated, this number is always finite, right? Because the number of elements in a ball is at most the generators to the nth power, right? So yeah, this is always fine. But yeah, I mean, it's a good exercise. So to see that, so the lemma is, yeah, if gamma GS equals 1 for some S, then gamma GS prime equals 1 for any S prime generating the same G. So this is a related, this follows from the property that we said before of the word metric being quasi-isometrically invariant, right? So the proof, right? So we know that the word metric of G with respect to say S prime is less or equal than C times the word metric of G with respect to S plus C for some C. And for any G. Right? And now, so if we know that the norm of G, so if G belongs, if the norm of G in S is less than N, then the norm of G in S prime is less than Cn plus C. Right? So gamma, so if we look at the growth rate, gamma GS of N is less or equal than what? So if we do that, the growth rate with respect to S prime, what do we have to write here? An elemental norm at most N with respect to S. It has norm at most Cn plus C with respect to this one. So then this you get Cn plus C. So what happens if we take the nth root? Right. So gamma of GS is the length loop of gamma GSN to the 1 over N is less or equal than the length loop of gamma GS prime Cn plus C over 1 over n. Okay. So this is also, yeah, is 1 over c n plus c times c n plus c over n. And so this is less or equal than gamma g s prime to the power c. And so, yeah, and the same is true, right? Yeah. So in general, is so right. So there exists a C such that indeed gamma GS is bounded by gamma GS prime C, and it's bounded by gamma GS prime 1 over C. So you see, the number gamma is not independent of the generating set. But whether it's 1 or not, it is independent because they're related at most by power. Okay. So another example, the group of exponential growth would be again the free group. Suppose you're looking at the free group in R generators, and again, S is the standard generating set. And so what would gamma GS be here? Yeah, is it R? Let's see, right? So remember that if we do the free group in 2 generators, what's the growth rate? Right, so remember that this is F2. So the growth rate here is what? What? And it's not 2 to the n, right? Because look, let's count, right? So suppose you're taking 2, for instance. Right. How big is the sphere? How radius? And in F2, the number of elements G says that the number of G equals exactly n is what? So this tree is what kind of tree is it, right? It's a now let's count, right? So n equals 1, you get, so n equals 0, you get 1, n equals 1, you get 4, n equals 2. Yeah, you get 4 plus 1, yeah, that's right. And then here, the next one, you get 1 plus 4. Okay, this are the, and here you have what? You have 3, 3, 3 times 4 times 3. Right? So this, yeah, if you do n equals 3, you get 1 plus 4 times 3 plus 4 times 3 squared. So this is, you know, every time you have three more elements than before. So this is 4 times 3 to the n minus 1. Exactly. So in general, yeah, in general, the free group of rank R right, is a 2r minus 1 regularly. So this is of the order of 2r minus 1 to the n. Right, because you have r generators and the inverses, so you get 2r, and then you have 2r minus 1 outgoing direction, and 1 is coming back. So again, what is the constant here is, okay, an exercise that one can figure out, but definitely this is a group of exponential groups. Okay, and so let me finish, then we can take a break. We can say the following proposition is that if G is a group of sub-exponential growth, and mu is finitely supported, then then the entropy of this measure is 0. So let's try to think about it, why that is the case. So why is that the case? So what is h mu, right? H mu is the limit of h mu n divided by n. But what is the relation between the entropy and its support? You have a measure on a set, finite set. This is a finite set, right? So if you have a measure in a finite set, what's an upper bound of the entropy? Log of the cardinality. That's right. So this is less or equal than the log of the cardinality of the support of mu n. Right? And so now what do we know about the support of mu n? That's right, because if you set S to be the support of mu, right? Even in fact, okay, maybe we have to add maybe some stuff just for if this does not generate, but it's okay. But let's suppose that the support of mu generates. Yeah, then what is the support of mu n, right? So the support of mu n the cardinality of the support of mu n is bounded above by what? By the growth of the ball, right? So we have this gamma GSN. And so, right, and so then h of mu is less or equal than the lim of log of gamma GS n divided by n. And this is just the log of small gamma, which is 0. So we see that the theory of the Poisson boundary for groups of sub-exponential growth, at least for finitely supported measure. Okay, let me say that. For finitely supported measures, it's somewhat boring because the entropy is always zero. So then the boundary is always trivial. So there are no other harmonic functions. Now, if we relax the finite support to infinite support, then indeed very rich things, complicated things could happen, especially in these groups of intermediate growth. So in fact, it's more complicated than that. Okay, so that's the relationship between the growth rate and the entropy. Now we have to still prove the entropy criterion, but we can take a break now. Maybe it's step 55, so maybe let's take a break until 11:05. So welcome back. Can you guys online hear me? Hello? Yeah, okay, good. Okay, perfect. So before we get started, some organizational stuff. So if you need a grade in this course, you have to do a final project. And in order to make sure that I include you in the list of people doing the final project, you should send me an email by Thursday. And then we will arrange on a meeting probably on Monday. I'll reply to you and we will arrange time to discuss on Zoom, but what would a good project would be. If you also have your own thing that you think is kind of related and you might want to still talk about it, you're welcome to propose some topic, but otherwise I'll suggest some list of topics, and probably on Thursday I'll probably post some list of possible topics. If you're done with the grade and you still want to do a final project, you could also say it to me. Then we'll see. If there's too many people, then maybe maybe you won't have time to present, but we'll see. Okay, very good. So now let's go back to the actual entropy theory. So we want to discuss the proof of the entropy criterion. And there's two sort of proofs. So the first thing, the first proof is based on the concept of Furstenberg entropy, which is also a very interesting notion of entropy. So that's why I also want to discuss that. And then the second one will be using partitions, and that's the proof of Kaimanovich and Vershik. But let's first discuss the Furstenberg entropy proof. So first of all, we define the Furstenberg entropy. So given so now this is associated to an action. So we start with B nu, a genius space. So a space on which G acts, and nu is a mu stationary measure. Then the Furstenberg entropy of this boundary. So I mean, it's not a boundary yet, but we think of it as a potential candidate for boundary, is the following. Is we denote it by H mu B nu. And that's the integral of on G times B minus log. So it's basically the Radon-Nikodym derivative. For technical reasons, we take the inverse here. So here you see we're taking the G is a group element Nu is, again, we have this boundary action. We have G acting on this B. And we pick a point X on the boundary. And then we have this measure nu also on the boundary, on the space. And then we're taking the Radon-Nicodim derivative of G inverse. It's okay, there's a minus and G inverse is some minor technical thing, but basically it's the log of the Radon-Nicodim derivative. And then you're integrating. And you're integrating both over X, which is a point on this candidate boundary, and on G, which is the group. Okay. So it's actually not completely clear that this quantity is positive, but it is. Again, that's a convexity fact. So a lemma is the following. And again, it's not completely clear. It's not maybe true in general that this is finite. But in a case that we're looking at, it would be. So we have the following assertions. We have, the first one is that H mu of B nu is non-negative. The second is that H mu of B nu is 0 if nu is gamma mu invariant, where gamma mu is the group generated by the support of mu. So you see that kind of makes sense, right? So if the measure is invariant, then G nu or G minus 1 nu and nu are the same. So the Radon-Nicodim derivative is 1. So then you're just integrating 0. Otherwise you get to a number which turns out to be bigger than 0. So, and also there's a third thing, which is 0 is less than this one, which is less or equal than the asymptotic entropy. So again, let's suppose let's say that H of mu is finite. Otherwise, still some of these things might be true, but just to avoid complication. So we assume that this is finite. So then as a consequence, this is finite, the integral is finite, everything. Okay. So okay, so let's see the proof. This is one is the classical integral using the log convexity of the log function. So using strict convexity of log well, indeed, okay, you integrate over G, you're integrating over B of this minus log dG inverse nu d nu x d nu x d mu G. Well, this is less or equal. You see that the average of log is actually is bigger. Sorry. Than minus log of the average. So here we're taking G. We're not doing anything to G. But we are doing minus log of the integral over B of this Radon-Nicodim derivative. So this is just by the Jensen's inequality, the expectation of the log and the log of the expectation. And there's a minus, so that's. And now, okay, now it's clear because what is this, right? So this is the integral of the Radon-Nikodym derivative. So it's just 1. So this is minus log of 1, which is 0. So this is 0. Okay, and now we also see, because the convectivity is strict, that this is only possible if there is an equality almost everywhere. So equality would imply that for every G in the support of mu, right? Because this d mu G is non-zero only if G is in the support of mu, then you need to have this one equal to that one, which would mean that dg inverse nu over d nu, right, should be 1 of x equals 1, nu almost every x. And so this, of course, implies that G inverse nu equals nu for every G in the support of mu. And then, okay, this G generates gamma mu by I mean, by definition. So this is implies, or is equivalent to say that G nu equals mu. Yeah, we can bring the G inverse to the other side. Yeah, the action of G is by measurable isomorphism, measurable invertible measurable maps. So you see G nu is absolutely continuous with respect to nu and vice versa. So G nu equals nu for every G in gamma mu. And so, well, of course, the inverse is even easier, because if this is invariant, then the Radon-Nikodym derivative is 0, and then, of course, you have equality. Even somewhat easier. Okay, so this is a very nice notion of entropy. And the other thing is the proof of 3. So proof of 3 requires a few more computation. So we say that if you start with alpha and beta probability measures on G, and nu a probability measure on B. And now we claim the following. We claim that H of alpha star B, B nu, this is, sorry, is equal, even equal, okay, even equal to H alpha of B, B star nu, plus H beta, B nu. So this is by doing a, just writing the log, splitting the log. So let's see how to do it. So if to prove that, we say that rho of gx is indeed minus log the G inverse nu over d nu x. And then we claim the following, that rho of G inverse G prime x equals rho of G prime x plus rho of G prime x. This is again, basically this is by the chain rule of the radon-Nicodim derivative and the log. So okay, this is, you can check. It's a co-cycle, typical co-cycle condition. Okay, and now once we have that, we basically integrate on either side, and we get the equality, right? Because H of alpha star beta of B nu is the integral of rho G prime x d alpha of G d beta of G prime d nu x. This is because if you remember the definition of push forward of convolution alpha star beta is the push forward of the product measure on the group by the multiplication operation. This is by definition of convolution. This is the integral with respect to alpha star beta. And then we can just do the computation here. This is, of course, this is the integral over G times B. And now we do the integral of rho G prime x d alpha G d beta G prime d nu of x, again, G times B plus the integral of rho G prime x. Again, this is, well, in fact, the integral with respect to alpha of G, we can forget about it because there's nothing to integrate. Then this is d beta of G prime d nu of x. So this is an over G dot B. So that's literally definition. And then what else you have to remember? Well, you have to remember the other definition of push forward. So if we take this product and you look at the push forward G prime x, this is the distribution of that is beta star nu. So this is literally what? The integral over G times beta B, right? Of rho of G y d alpha G d beta star nu of y. If we let y to be G prime x. And this is, okay, this is by definition is the H of beta of B mu. And this is by definition H of alpha of B with the measure beta star nu plus H beta B nu. So it's a somewhat lengthy computation. It's very satisfying that, in fact, all the pieces fit together. This is like really, it tells you that the definitions are sort of put forward very carefully so that the pieces do fit together very, very nice. Okay, and then from there, so recall, so what do we need to show? We needed to show, so we want to show that H mu of B mu was less than H mu, which is the, again, the limit of H of mu star and for convolution, right? Okay, and so we have to just do this over and over. So we let so okay. So we let alpha to be mu n and beta to be mu. And so we get H of mu n star mu of B nu is equal to H of mu n B mu star nu plus H mu B nu yeah, and in fact, yeah, and mu star nu is new, right? So since B is a mu space, G mu space. Right. So this is H mu n B nu plus H mu B nu. This is true for every n. So by induction, you get that H mu n B nu less or equal than n H mu B nu. I mean, this is, well, it's literally equal. You know. It's just equal. Yeah. It's literally equal, right? Right. Yeah, because otherwise, yeah. So then we have, yeah, exactly. So H mu of B nu is equals to H mu n B nu over n. And now we just have to say that for any for any space, this is less or equal than the measure the entropy of H on the group itself. Well, I think we haven't quite shown it yet, right? It's yeah, so right. So this is also should be an application of Jensen's inequality, right? So for any say beta on G, we want to say that the integral of G times B of minus log D beta inverse nu d nu of x d dg, sorry, dg d nu of x d beta of G is less or equal than, yeah, than the sum, then the minus sum of beta of G log theta of G. Right? So again, I think this is just an application once. Yeah, this is once again an application of the Jensen's inequality, like this one less than this one. Yeah. So yeah, so this is just this. Okay, so now right. So now we have the for any measure, this is less of this, and then so we take the limit. So this one converges to H of mu. So very good. Okay, so this is a preliminary idea. So in particular, why is this Furstenberg entropy useful? So recall the following, right? So recall that any mu boundary, we gave this definition before, is a quotient of the Poisson-Furstenberg boundary. Namely what? Well, we need, namely, there is a map, there is from B Poisson, mu Poisson to B nu. There's always such a projection map. So yeah, so for any, so this is true for any mu boundary. B nu. And in fact, yeah, so in fact, this map is not just projection map, it's also G equivariant. Yeah. So let's say phi such that phi star of nu p is nu and phi is G equivariant. So if we have a projection like that, we saw that projection decreases the entropy. So in particular, if you compute the Furstenberg entropy, H mu of B nu is less or equal than H mu of BP nu P. And the Poisson-Furstenberg boundary is a mu boundary, so it's a mu space. So this is less or equal than H of mu. So this is the lemma that we saw before. So for any boundary, the entropy of that boundary is less or equal than the asymptotic entropy. Moreover, for any other mu boundary has even smaller entropy. Precisely because there is this quotient. So this quotient can only reduce the entropy. So in fact, the search for the Poisson boundary in this context can be said in the following way. If you can find the new boundary which has the highest possible entropy, this must be the Poisson boundary. Because because for each of them is like that. And then if you have an equality, again, there is the strict convexity. So if you have two boundaries with the same entropy, then they have to be isomorphic to each other. Okay. So what's the idea of this entropy, the proof of the entropy criterion using this Furstenberg entropy? Well, let's see. So if H mu is 0, so if the entropy of the whole walk is 0, then, well, the entropy of the Poisson-Furstenberg boundary is less or equal than 0. So it must be 0. So this implies that this boundary has to be a point. Right? I mean, we can. So in particular, we can say that G star nu P equals nu P for any G in gamma mu. In fact, we assume that gamma mu assume. Yeah, we have to assume it that gamma mu equals G. It's part of the thing. So cannot say anything about the part of the group that is not in the support of the walk, because you cannot tell it from the walk. So okay, and so this map, so this every measure, so this measure is G invariant for every. In fact, you can even from this you could directly argue that this is isomorphic to a point, actually, by Jensen's inequality. Or you could also argue like this. So recall the Poisson transform. So the Poisson transform again goes from L infinity BP nu P, and it's an isomorphism with H infinity G mu. And how is that defined? Well, it's defined like this. So you start with F, and then phi of F of G is the integral of F dg nu P in this case. Yeah, like that. Over V. But now if we know that nu is G invariant, this does not depend on G anymore. This is just the integral of F of the nu P. For any G. So it's constant. So phi F is constant for any F in L infinity. So clearly this means that H infinity, because it's isomorphic, then this must be just R. Again, the G invariant is equivalent to the boundary being trivial. So this measure is G invariant. So that's the direction from H, the entropy being 0, to the boundary being trivial. Now the other direction is not hard, but actually, we will use a step that we haven't proved yet, but we're also going to give another proof. So we'll see. But okay, so the other direction, so vice versa. Let me say the argument here. Vice versa here is that if the boundary is trivial, Bp nu p, it's isomorphic to a point. Well, then clearly this measure is equivalent G star mu p equals mu p for every G. Because there's only one point. This measure is a delta mass, so it's equivalent, right? So the Furstenberg entropy of the Poisson boundary is 0. Now this proof at the moment, so in fact, so we need one more lemma, which is not just the inequality here, but there's an actual equality here. Is that, again, if G is countable, let me write it like that, because we can define the Furstenberg entropy for a non-countable group, but we don't care at the moment. And again, the entropy is finite, then the Furstenberg entropy of the Poisson boundary equals h mu. I mean, to do this, you basically you have to look at BP. Again, BP is a quotient of the space of infinite sequences. So you can look in at the action of G on the space of infinite sequences on itself, and you do that computation, and eventually you get the same. You get that this is the original definition of its entropy. So let's say that we assume this for the moment. So if we assume this from the moment, then we're good to go, because from this one being 0, this also implies that h of mu is 0. So again, the point of view from the point of view of boundary theory is that the Poisson-Furstenberg boundary is the largest possible boundary. So it's the boundary with highest possible entropy. And in fact, this entropy is exactly the entropy of the walk. And now, so if the entropy of the walk is 0, then the entropy of the boundary has to be 0. And so the boundary has to be trivial. And vice versa, if the boundary is trivial, then its entropy is 0. And so the entropy of the walk is also 0. This is more or less the idea. So this proof more or less is following the Rienich proof, actually. So the other proof is the Kajmanovic and Vershik proof that we will actually see, because it's also very useful, in fact, even more useful for generalizing it to the non-trivial part, to the non-triviality, but just identification problem. So let's see. So the second proof of entropy criterion and this uses partitions. So, and conditional entropy. So the idea is this one. So we start with a Lebesgue space XM, a Lebesgue space. So a nice measured space. So in particular, it could be the space of infinite paths. This will be always our favorite one. And then let you take two partitions, psi and eta, be partitions. Are psi incountable countably many pieces, basically. Begin with. Well, let's say we start with that, but then it will become more complicated. But okay, at the moment, we start with that. Okay, so now we want to know. So what is again how to think of a partition? It's again is an outcome of an operation. So the first partition psi does some experiment, so subdivides the space in basic some bunch of outcomes, and then the second partition, the eta partition, partitions the space in some other way, which is intuitively corresponding of doing some other measurement. And now the question is whether these two events are independent, right? So they define the conditional entropy. The conditional entropy of psi with respect to eta is the following: h of psi conditioned on eta. Like this is minus the integral over x of log, and now you're taking the relative distribution. So it's the measure of psi of x intersect eta of x divided by measure of eta of x dmx. What is eta of x and psi of x? Where psi of x is the element of psi containing x, right? So we pick a point x, and so x is in some cell for a psi. This is psi of x, and is also in some cell for eta. And now we want to do a conditional probability. So suppose we already did the experiment eta, we already know what is the outcome is eta of x, which has certain probability, and so then we do the conditional probability with respect to this prior. So just the measure of the intersection divided by classical conditional probability. So again, this is, if everything is countable, this is easy. Now when you're taking limits, things get more hairy. But for the moment, we start with countable ones. Okay, so indeed, so you want to say, note the following, that psi and eta are independent. Dependent partition if, well, by definition, the measure of psi intersect eta equals the product, the measure of psi and the measure of eta, right? And clearly, this will bring this integral to zero, right? So this is if and only if h psi given eta is 0. Right? Again, there's a usual convexity issue. If if they're not independent, then there's a counterexample, and then you look at the counterexample and okay. So now, what are the partitions of interest for us? So we consider a random walk. So consider you consider omega p space of infinite paths. And we want to introduce some partitions. Yeah.
So the independent.
Yeah.
If the log becomes log and the zeta x, right?
The log, yeah, so
Log m zeta x, y integral 0.
I guess, wait, yeah, right, so we have to normalize, right? So
What I would have thought is that depending on an h zeta condition on a would be h zeta.
yeah, I think you're right. Yeah, sorry. Yeah, right, because this, yeah. Yeah, in fact, it's the what's intuitive. Yeah. Yeah, that's right. Okay, so yeah, sorry, I'll fix that. So now, we have these two partitions, and so we have this infinite paths, and we have to construct partitions. And so given n, we have two partitions. So we have the head partition, call it alpha n. And the head partition is like that. It's like you do Wn is the same as Wn prime, sorry, or Wm, sorry, same as Wm prime if these paths are the same up to step n. So if Wk equals Wk prime for all k less than n. So meaning really the two paths at the beginning, the first n steps of the paths are all the same. In fact, this is equivalent in our recalling our notion of recalling that, yeah, we call Wn G1 Gn. So these are the increments. This is the same as Gk equals Gk prime for all k less than n. Because, well, G1 is W1, and W2 is G1, G2. So it's equivalent to impose that these are the same. Okay. Yeah. Moreover, so you notice that these partitions are like finer and finer, right? So note that alpha n plus 1 is, we call it bigger than alpha n, meaning finer. meaning that, right? So if points that are, yeah, so the points that are separated here, they will also be separated here. So these classes are some further subdivisions of the classes of those. And so we think of this as being bigger because the entropy, you see, if you further split things, the entropy grows. So that's why. So this is the usual notion of partitions, but it's kind of maybe slightly counterintuitive, but the pieces become smaller, but we call it bigger partition because you have more information. Now the other one is the tail partition. So the tail partition is recording the tails, as the name suggests. So we say that Wn is in the same eta, you see, or Wn eta n class of Wn prime. If, well, Wm equals Wm prime for m, for all m bigger than n. So in this case, you have a path and you have another path. And this path start at some point they coincide from there on. And so the issue, so the real tricky point is this: you define the tail partition, the asymptotic tail partition. Eta infinity, which is the infimum of the eta n. So note, so this is the tricky, again, very tricky definition. Unfortunately, whenever you have the possible boundary at some point, there is a non-explicit step that has to be. So here, what's going on here? So you see here, if you look at eta n plus 1, this is coarser than eta n. Right? Because two elements could, be different at step n and become the same at step n plus 1. So as n gets larger, these partitions get coarser and coarser with less and less entropy. And now this mysterious object here is the coarsest, is the, well, is the finest measurable partition. This is very, very important. So again, remember that we have this theory of measurable partitions that I discussed when I was on the iPad. So this is very important, tricky point. The measurable partition that is coarser than all eta n. So again, here we see, again, this definition of Poisson boundary that I gave you, which is we introduce, so this is slightly different because, so here we're quotient paths that coincide for after some time, for in a synchronous way. So you want at the same time to go. So the definition that I gave you before, there were two paths that are allowed to coincide in an asynchronous way after different number of steps. But it turns out that for groups, only for groups, the two definitions are equivalent. And in particular, this one is like synchronous tail partition. And now the Poisson boundary is given by quotienting out classes of this, again, equally mysterious partition. So that's why, again, it's kind of really non-constructive, but that's what we want to get a handle on. So let me just state the last word, and then next time we will finish this proof using partitions. So we note the following. We note that the Poisson boundary here, by definition, or well, it also is again omega p quotient by this eta infinity mysterious partition, and so, but fortunately we can control the entropy at each finite stage, and then taking a limit. So that's why it's easier by looking at the entropy rather than looking at these partitions. Okay, yeah, question?
With offset, we show like Wn equals W prime and plus one.
Yeah.
Then these are not separated by this partition, and then it's the behavior, right?
Correct.
So this,
So yeah, so there is one point to be made, which is correct, which is a priori, yeah, the original, the other one, the asynchronous one, has larger equivalence classes. But for groups, again, if you Markov chain as group invariant, like for random walks of groups, it turns out that the quotients are still isomorphic. This is not completely trivial, but it is still true in this situation. Yeah. More questions? Okay, then I'll see you on Thursday. Send me the email if you're interested in the final project.